Great. Hi, everyone. Sorry I can't be there in person, but thanks a lot to the organizers for organizing this great workshop and for all of you for listening to me. All right. So you've heard a lot about DESI, presumably recently, and I just wanted to tell you a little bit about what we can do combining CMB and DESI galaxies, and I think it's very powerful, and I hope to convince you of that. So let me start with one slide about DESI. So what's DESI is the Dark Energy Spectroscopic Instrument, is a spectroscopic survey with 5,000 robotic fibers and covering about 14,000 square degrees initially. We started in 2021, where we have about a couple of years left. And the goal keeps sort of with a moving target. It keeps going up, which is great. Right now, we think we'll end the survey with about 50 million redshift of galaxies, split in this way. Actually, these numbers here should be revised up a little bit, but we have a bright galaxy survey at low redshift, as very dense sampling of the local universe. Then going a bit further up, redshift 0.4 to 1, we have the luminous red galaxies, or LRGs. I'll be talking about these a lot. At higher redshift, we have emission line galaxies, the galaxies that selected on the O2 emission line up to redshift 1.6. And finally, at even higher redshift, we have quasars and Lyman alpha forest. So to date, we've already collected, we're analyzing the first year of data, and the results that you see coming out is usually about the first year of data. However, in the CAN, we already have 3 years of data, which is about 30 million galaxy spectra and 10 million stars, okay? So we'll be moving on to analyzing that year 3 data very soon, as soon as we are done with year 1. Okay, in addition to the spectroscopic data, I want to advertise that we also have a very good photometric sample, and these photometric samples are the targets for the spectroscopy. However, they cover the full footprint of the survey and more. So basically what we cover with the photometry is anything that is not black and white on the map here on the right. And especially these LRG samples, we split into 4 photometric bins, which you see here. This covers about 20,000 square degrees already. And we have spectroscopic calibration for all of them. We have, as I said, 30 million spectra of galaxies, so we can get this N of Z, essentially redshift distribution, extremely well. So, you know, calibrating sort of redshift distribution is a problem. Also, they come with very good PhotoZs, and this is in work led by Ron Pujo and myself. And these are all public, so you can look for this paper and download the catalogs and use them. And they also come with very good PhotoZs, as I said, and the properties and systematics are well understood. And moreover, soon there will be 2 more bins at lower redshift, what we call this by galaxy sample, or BGS, at redshift 0.2 and 0.3. So a lot of the work that I'll be showing will be relying on this data. All right, but you say, how come, you know, redshift galaxies, DESI galaxies are redshift 1, while the CMB is at redshift 1000? How come, you know, they have anything in common? As well, is because, of course, the CMB photons had to travel all the way from the surface of last scattering, where the CMB is emitted, all the way to us. And we know that there are scattering and gravitational processes that leave an imprint on the CMB. So in a sense, CMB is a 2-dimensional map, but is a map of the entire observable universe with an asterisk here. And the asterisk, of course, is if you have good enough resolution, because this, you know, these imprints are imprinted on the scale of a galaxy, for example. So you want to be able to resolve the typical galaxy or have sort of arc-minute type resolution to be able to, you know, make full use of this information. But indeed, we have maps that are you know, with that resolution, so we can do do this as I will show in a minute. Opportunities from DESI across CMB. Well, DESI has a large overlap with both Planck, about 17,000 square degrees at the moment once you mask the galaxy, and also ACT, the Atacama Cosmology Telescope, which we have an overlap of about 9,000 square degrees with. Because of these synergies between especially ACT and DESI, we have negotiated an MOU between the two collaborations. This took a while. I led a lot of this effort, and now it's coordinated by myself on the DESI side and Manushan on the ACT side. We have tens of projects ongoing, focusing on anything, basically any secondary anisotropy of the CMB, anything that is created after the CMB was emitted. We have several projects on that, and I will give you a couple of examples later. I'm happy to say that the first round of papers will be in a few weeks, so stay tuned for those. But let me jump in. So let me give you two examples of what's coming in a few weeks. The part one will be imaging the gas with CMB as a backlight, and part two is CMB lensing cross correlations. And again, I should stress that this is only a small and biased subset of the ongoing work. Okay, so let me start with talking about using the CMB as a backlight. So this is there are several effects that are due to Thomson scattering. One is the kinematic Sunyaev-Zeldovich effect, which is basically just the Thomson scattering of CMB photons when they collide or they scatter with a galaxy that has a certain peculiar velocity. The temperature fluctuations created by the kinematic Z effect is proportional to the column density of electrons, or if you can think about it, the gas profile of the galaxy, times the radial velocity. So this is really the product of something that depends on astrophysics times something that depends on cosmology. And for the purpose of this talk, we'll be using it to get the number density of electrons, the gas profile. However, there's a whole set of papers on KZ cosmology as well, which I won't get to today, but feel free to ask me later. Then there's also a thermal effect, which is proportional to the product of the number density and temperature of the electrons. So you will recognize this as the thermal pressure, hence the name thermal SZ. There's also a patchy screening effect, which has been detected recently. It's proportional also to the number density of electrons. So in a sense, it measures very similar quantity to KZ, just a little bit smaller. So why do we care about? I said I was focused on the astrophysics today, and why were we interested in this electron or gas profiles? Is because baryons are 16% of the mass in the universe, and to do lensing to sub% level with the current and future surveys, we need to know where 16% of the mass is, and moreover, we know that this is a scale dependent. This baryons, we know from simulations, they lead to a scale-dependent suppression in the matter power spectrum. So this is very relevant for a dark matter conference because, finding a suppression compared to dark matter-only simulations doesn't necessarily mean something is wrong with our dark matter model, but it could be due to baryons. And the good news is that I will try to persuade you that we have a good avenue to map where the baryons are, and we can definitively say, where they are and what their effect is on the matter power spectrum, such that any other deviation could be new physics, for example. Okay, so let me show you what, first of all, some published results. So this is something that led by Manushan and myself back at the height of the COVID pandemic, and it's something I'm sort of still very proud of. So we have KZ measurements of both galaxies, and the y-axis here you can interpret it as basically the cumulative abundance of baryons that are enclosed within an radius r, compared to what the dark matter would look like in an FW profile up here. You see that you're towards the center of the halo. There's way less baryons than there is dark matter, in particular the virial radius here, about a couple of arc minutes. You see a large deficit. This is nothing but the missing baryon problem. while if you go out in the outskirts, you see that you recover the full cosmological abundance. Of course, as we expected, baryons have not disappeared. They've just been pushed to the outskirts of these halos. By feedback processes, but this can sort of almost directly be turned into predictions for what the suppression in lensing looks like. But we also measure the thermal Sudnyaz-Zadovich effect, or the pressure. And once you have density and you have pressure, of course, you can get temperature in a model-independent way. And you can solve, once you have lensing measurements, you can really solve for the full thermodynamic information of the halo. But this was back in the day, and there was BOSS. So let me talk to you about DESI a little bit. So we're, as I said, we're analyzing the one data now. As you've probably all seen, the BAO results are out already. We have 2 more years of observations remaining, plus possible extensions, and there are lots of ongoing projects, including related to what I just showed you before, and the fact that DESI will have about 40 times the number of spectra than BOSS really allows us to take these measurements to the next level. Okay, so what I'm going to talk to you about is with the dream team of the people shown here. Bernie from graduate student at Stanford, Henry, graduate student at Berkeley, Boriana, postdoc at Berkeley, and then Manu Slack, and myself. And there are also other works by other groups that I'm not showing here, but it's important to acknowledge. So we are using both photometric galaxies and the spectroscopic galaxies that I talked about. And let me give you a sort of sneak peek, very preliminary, so shouldn't take too many conclusions out of it, but it's good to show the power of sort of DESI data for this type of science. Here is an example of these DESI photometric LRGs, those bins that I was talking to you before. Actually, with public ARC data, this will get much better very soon with the proprietary ARC data, which we're using in our analysis, so that the paper should be out in sort of a month's time scale. But what I wanted to show here is that now the data, which is in red, is good enough to distinguish between 2 popular simulations, or 2 popular models of feedback. One is that in the blue line is blue dashed line is the TNG. Think of it as Millennium TNG or Lustrous TNG, the TNG suite of simulations, versus, for example, the old Illustrious, right? And quite intriguingly, the kind of common wisdom is that the old Illustrious has way too much feedback. However, this is not, and those statements are generally based on stellar masses or colors. However, when you look at the gas directly, at least for this mass bin, at least for this redshift bin, I'm not making general statements here, but it seems to, fit the data better. And of course, we disagree with the dark matter simulations at over 40 sigma. The baryons don't trace dark matter. That's not too surprising. However, as you can tell, now we have good enough statistical power to be able to distinguish between different simulations. This statistical power, this I should say is a paper led by Boriana and myself that should be out soon, and there's equivalent papers on spectroscopic samples and on TSE that I'm listing here. But this data is good enough that now we can measure this as a function of mass, redshift, luminosity, and you name it, and this will help us enormously when you are trying to calibrate lensing. So again, I'm giving you a sneak peek here. In 3 stellar mass bins. The lowest stellar mass bin is the blue curve, and then we go to an intermediate one with the orange curve, and finally the most massive sample. So first of all, of course, the amplitude of the signal depends on mass because we are looking at the gas here. So that's not surprising. However, you can tell that the shape depends a bit on mass too, which is very interesting, and characterizing the size of feedback as a function of all of the halo properties. Is sort of the name of the game going forward. So we hope to soon have predictions for the matter power spectrum, as well as constraints on halo thermodynamics and KZ cosmology. Okay, so in the last 5 minutes, let me tell you about another thing, which is CMB lensing, and I'm going to use this slide also to advertise that the beautiful ACT DR6 lensing maps are now public, and they're available on the Lambda website here. You'll find them in the slides, so you can use them for your favorite project. Okay, so as you all know, the current state of affairs is a bit confusing, and lensing measurement is a bit confusing. You have primary CMB here at the bottom, giving a relatively high value of sigma 8 or S8. CMB lensing seems to agree very well, but the number of galaxy lensing measurements, especially based on photometric redshifts, seem to sometimes come out a little low. Sometimes they are quite good agreement with Planck. So the question is, can we understand this? And this again, I'm showing the team up here. This work is really led by two graduate students at Berkeley, Noah Saylor, and UPenn, Joshua Krim. So we're going to use the spectroscopically calibrated 4 samples that I talked to you before. So we have 4 redshift bins between redshift 0.4 and 1, full spectroscopic calibration. This means that we are immune from photo-Z errors because both the CMB, the source is the CMB, and we know the redshift of the CMB very well, and we also know the redshift of the lenses very well. So we have no photo-Z errors, but also the CMB lensing is independent of shear calibration, intrinsic alignments, and other properties. So we thought it would be extremely interesting to check, what we would get with this, since these are common sort of worries with galaxy lensing. We have very high redshift success rates, which means that basically we don't need to do any photo-Z marginalization. We use a hybrid effective theory model for modeling the data. So this we see this as highly complementary to cosmic shear or galaxy-galaxy lensing measurements. Of course, we measure this cross correlation between Planck and ACT and DESI galaxies. So I'm showing here, these are good fits. In black is the sort of best fit curve. You see all the data points regardless of the CMB, which Planck map, for example, you choose. It's quite independent. And the galaxy autopower spectrum is also well fit by the theory. And this is, I should say, of course, is very preliminary. I won't go through this slide, but of course, in the 70+ page of the paper, 2/3 is about understanding systematics, because this is the name of the game in modern cosmology. Often these measurements are systematic dominated. However, after extensive study, we find no evidence with statistically significant systematic contamination. So I won't go through this slide. I'll let it out. I have it in my slides for the discussion later if anything comes up. But let me go to the bottom line, the results. I got permission from ACT to show you these preliminary results. Again, this will come out in 2 papers in a couple of weeks, hopefully, led by Noah Saylor and Joshua Kim. So these new measurements are the 4 points in purple. These 4 points, they come out a little bit low once you combine them all. We are about 2 sigma low compared to Planck, which is interesting. And I think what's kind of this is similar statistical power to galaxy lensing. So we're talking about constraints at the 2.5% level. As I said, it's immune to photo-Z uncertainty, intrinsic alignment, shear calibration, etc. There will be 2 bins that will be added here very soon. And this is kind of very interesting because you see that this lowest redshift bin, the 0.5 bin, seems to be the one that is most discrepant. This is intriguing because this is where dark energy starts to become important, dynamically important, right? And in particular, the region which is dark energy dominated is this region where I'm saying, DESI BGS is coming soon, okay? So those points will be particularly interesting because if anything is going wrong with dark energy, that's where it would show up, okay? So this will be out soon, as I said. The next steps is, of course, combining with the 3D clustering of DESI. That's where DESI really shines. This combination breaks the degeneracy between galaxy formation bias parameters and cosmology. And if you do it in 3D, you have much better degeneracy breaking than in 2D. And finally, we want to study the scale and redshift dependence of the signal, and as well as beyond lambda CDM physics, including, of course, neutrino masses and other extensions. So let me conclude here, since I'm out of time. I hope I persuaded you that there are many opportunities from combining DESI with the CMB. We can map the gas with the Synergies effect and take these measurements to a next level. And there's also great potential for combining CMB lensing and galaxy clustering for measured growth of structure, neutrino mass, and possible extension to lambda CDM. So thank you very much for listening, and I'll end here. Happy to take any questions. Thanks.